Hi everybody, I hope this video finds you well. In today's video, we're going to be giving a brief introduction to the Laplace transform and how it applies and helps with differential equations and IVPs. Now, this video is not intended as an in-depth discussion of the Laplace transform. There is a lot to learn and consider with the Laplace transform as a mathematical transformation, as a mapping. There's lots of theorems that we're going to talk about in this video that we're only going to briefly mention why they should be believable. We're not going to be giving full proofs of them. So again, this is really meant as just a quick overview of the Laplace transform rather than an in-depth investigation of it. Our end goal and what you will be able to do by the end of this video is you should be able to understand what the Laplace transform is and then also how it applies to differential equations, specifically IVPs, and allows you to convert from something that is a differential equation into an algebraic equation. So let's get started with the definition of the Laplace transform. So the Laplace transform is a mapping that maps a function of one variable. Usually out of convention, the initial variable is t, but it could really be any sort of independent variable that you're using, t, x, whatever. And it maps functions of that single variable to functions of another variable. Again, usually out of convention, it changes it into the variable s. So we will be starting with functions generally of t, and we will be transforming them into functions in terms of a different variable, usually s. Now, initially, it might seem a little intimidating when we're talking about a mapping that maps functions, but keep in mind that you have encountered in the past other transformations that transform functions into other functions. A great example of that is the derivative, right? If you take, say you start with the function f of x equals x squared, you can think about the derivative as the mapping that sends the function x squared to its derivative, which would be 2x. So we've encountered the concept of the transformation of a function before. The Laplace transform is just another example of that. So how do we define the Laplace transform? Well, we give this definition here. It's based on what we call a type 1 improper integral. The Laplace transform of f of t is the integral from 0 to infinity of f of t e to the negative st dt. Now, if you notice this here, right, once you were actually to perform that integration to find the antiderivative there, then this is an improper integral, so you'll be converting this 0 to infinity into a limit of a definite integral. We'll sort of see that in a moment in an actual example, but the main thing to keep in mind is that since this will ultimately be a definite integral in terms of t, once you've taken that antiderivative and plugged in the bounds, t will no longer be present. The only variable that will remain is that s, and that is why it will have transformed it into a function of that new variable s. Let's go ahead and actually just immediately start with trying to perform a Laplace transformation. We'll see that in the long run, at least from our perspective, we won't often use the definition. We'll sort of introduce a table of common Laplace transforms. But let's go ahead for right now and just actually try to do one manually using this definition. So we're going to attempt to determine the Laplace transform of e to the t. So we've got our Laplace of e to the t. What we need to do is that will be the integral from 0 to infinity, e to the t, e to the negative st dt. Let's go ahead and immediately deal with the improper integral. Remember, every type 1 improper integral should be viewed as a limit of a definite integral. So we're going to introduce just a parameter to deal with that. A lot of times, maybe in a Calc 2 class, the parameter you used was t, but of course that's already in use. So we'll use something for the purpose here like r. So we'll have as r goes to infinity, then the integral from 0 to r, e to the t, e negative st dt. Now again, in terms of what we need to do, remember you sort of work from the inside out. You need to go ahead and determine the antiderivative, then plug in the bounds, then apply the limit, and then we will be done with this improper integral here. So let's go ahead and simplify the integrand a little bit. That's the limit as r goes to infinity, and we have our integral 0 to r. Since they both have a base of e, we can go ahead, and since they're multiplied, we can add those exponents, and we'd end up with minus s plus 1 times t, and then dt. Now that is an integral we can go ahead and do. We know that antiderivative. Technically, we're doing like a little mini u sub with u being negative s plus 1 times t. But remember, negative s plus 1 is being treated as a constant, right? It's not the variable that we're integrating here. So we know that this is going to come out as 1 over minus s plus 1 e to the minus s plus 1t evaluated from 0 to r. And again, if you're a little unsure about that, just go ahead, write out the u substitution, and you'll see that that should make sense there. So we get our limit then as r goes to infinity, 1 over s plus 1. Let's go ahead and plug in our bounds. And as we do that, we get r there, and then minus 1 over s negative s plus 1. When we plug in 0, we get e to the 0, which is 1, so we're just left with this expression here. Okay, now let's go ahead and focus on this portion here. The limit is as r goes to infinity, so it's applying right in here. Obviously, the behavior of this is going to depend in terms of whether or not it is going to converge or diverge. We are only going to be interested in places where it converges. If it diverges, then that improper integral doesn't really make sense, and that Laplace transform doesn't really make sense. So we're interested in when this is going to converge. Well, obviously, as r goes to infinity, this is going to infinity. So it's really going to depend on whether or not this negative s plus 1 is positive or negative. So let's go ahead and make sure that that is negative, so that that overall exponent is actually going to be headed towards negative infinity, because then we know that e to the negative infinity approaches 0. If this negative s plus 1 here is positive, then this whole thing is going to be approaching positive infinity. E to the infinity, of course, goes to infinity, and it's going to diverge. So let's go ahead and just make the assumption. We'll just let s be greater than 1. If s is greater than 1, then this is guaranteed to be negative. Then, of course, this entire sort of section here is just going to approach 0. And of course, we still have our other component there, minus s plus 1. And of course, simplifying that, we get 1 over s minus 1. So what we've just determined here is that the Laplace transform of e to the t is now the rational function 1 over s minus 1, provided that s is greater than 1. Now again, in terms of the computation, we're not going to be doing a tremendous amount of Laplace transforms by definition. Nobody really does a tremendous amount of them because in terms of feasibility, as we'll see, it's a lot easier to have a few basic cases and then know how to manipulate from there than it is to be using this definition over and over again. But the main thing you want to keep in mind here is that we started with a function of t, in this case the exponential e to the t, and we ended with a rational function 1 over s minus 1 in terms of a new variable. Okay, let's talk a little bit more about some properties and things that are true about this Laplace transform. We also should probably mention, as we had to sort of analyze here with this letting s greater than 1, when does the Laplace transform even make sense? Are we able to take the Laplace transform of every function out there? Are there certain situations where it doesn't work? Let's talk about those. So, we're going to talk about some properties and facts about the Laplace transform. First of all, a theorem here, the Laplace transform is a linear transformation. Depending on where you're at in your mathematical career, you might have encountered the concept of a linear transformation. If so, you immediately know what that means. If not, all that basically means is that if the Laplace transform exists, then it distributes over addition. So the Laplace transform of f of t plus g of t is the Laplace of f of t plus the Laplace of g of t. So you can imagine that the Laplace transform distributes over addition. It also distributes past scalar multiplication. So the Laplace transform of a number times a function is that number times the Laplace transform of that function. Now, these two things, as mentioned, we're not going to be getting into the proofs of these different statements. This one is not a particularly hard one to prove, though. You should basically be convinced of this by the fact that you know that integrals distribute over addition and distribute past scalar multiplication. Since the Laplace transform is based around an integral, then it should have the same properties there. And you should be comfortable proving those results just by using the definition of the Laplace transform here. It's a good exercise to try, and I really recommend it. For now, though, we're going to move a little further down and give a definition that answers the other side of what we sort of mentioned. When does that Laplace transform exist? So this requires a definition that you may have encountered back in like a Calc 2 class. If you don't remember it, that's all good. We're going to redefine it here. So a function is said to be of exponential order if there exists constants m and a such that the absolute value of the function is less than or equal to m times e to the at for t greater than 0. Now, this is a pretty, I would say, complicated definition. It has a lot of moving parts. What you basically are saying here is something is of exponential order if you can basically bound it above by an exponential function. Most of your common functions, like the exponential, like polynomials, sines and cosines, all of that stuff are of exponential order because you can certainly find an exponential function that outpaces them provided you choose a large enough initial constant and also you choose like a large enough exponent there. Some functions out there are not of exponential order. You imagine something like e to the t squared. That is not of exponential order because that is going to move more quickly than any normal exponential because in the exponent you have a t squared rather than just a normal a times t something times t there. Some of you guys might remember the concept of like exponential order. You encountered this a little bit if you took a Calc 2 class and you talked about like series and the different rates at which expressions grow. People might have said that, logarithms grow the most slowly, then polynomials, then exponentials, then things like the factorial and beyond. When we're talking about exponential order, we're basically thinking about things like exponentials, polynomials, trig functions, logarithms, and everything that's slower than those. Again, for our purpose of this introduction, we're not going to go too much further into this, but one important note is that if f of t is of exponential order, then that means you can find some exponential function, e to the negative st, that because the function is going to be less than that, the limit as t goes to infinity is of f of t times e to the negative st is equal to 0. In other words, you can find some value of s greater than that a so that this limit will come out as 0. Now this really is the key note here because as we'll see in a few minutes when we talk about how you do the Laplace transform of the derivative, this fact is going to be really important. All right, another sort of theorem related to this exponential order. Again, we're going to just state this without proof, but it's a good thing to just sort of think about. It says that if f of t is piecewise continuous and of exponential order, then the Laplace transform exists. So this theorem, again, we're not going to prove it right now in this lecture video, but this basically tells us when the Laplace transform makes sense. You need your function to be piecewise continuous. That's a very weak condition. It just means that you can have discontinuities as long as each piece is continuous. So you have, finite breaks, finite jumps, things like that in your function. And it has to be of exponential order. As long as it satisfies those two things, then the Laplace transform exists. That means all your sort of basic functions, linears, polynomials, exponentials, sine and cosine, all that stuff has a Laplace transform. Let's go ahead, speaking of that, and look at a table of some common Laplace transforms. We're not going to calculate these, we're just going to state them and then make use of this. So here are some common Laplace transforms. This basically gives you the Laplace transform of a constant, the Laplace transform of a polynomial, the Laplace transform of an exponential, and the Laplace transform of your sine and cosine. So as you're working with the Laplace transform, feel free to make use of this table so that you don't have to go through and redo these. If you want to try some more of these on your own, you certainly can using the definition, but going forward, we're going to just use this table so we immediately know how to do these types of transformations. Let's do an example and just make use of this table and remember that the Laplace transform is linear and how that sort of is going to help us. So let's try to actually calculate using this table, this Laplace transform. Now, we're not going to use the definition. We're not going to write this as the integral from 0 to infinity of this whole crazy mess times e to the negative st dt, and then put an integral and do all that. We're not going to have to do all that. We're just going to make use of this table and the fact that it's linear. So if we're trying to do the Laplace transform of cosine 5t minus e to the 3t plus 2t squared, the first thing we want to remember is that the Laplace transform distributes over addition. So we can write this as the Laplace transform of cosine 5t plus the Laplace of negative e to the 3t plus the Laplace transform of 2t squared. Then remember that it also not only distributes over addition, but it also distributes past constant multiplication. So we can write that as the Laplace of cosine 5t minus the Laplace of e to the 3t plus 2 times the Laplace of t squared. Now we'll just use our table for each of these. So for this, the Laplace of cosine of 5t, that we'll be using right here. The a will be equal to 5 in this case. So this is going to be equal to, if we're doing that, we'll get s over s squared plus 5 squared. And then we'll have our minus doing this one here, the Laplace of e to the 3t. We'll be making use of this guy right here with a being 3. So this is going to be 1 over s minus 3. And then we have plus 2. And then we'll be doing the last one here, L of t squared. That one we'll be using this. We'll be using n is 2. So we'll be getting 2 factorial over s to the 2. Just putting all that stuff together and simplifying a little bit, we get s over s squared plus 25 minus 1 over s minus 3 plus, well, that 2 factorial is a 2, so we get 4 over s squared. And there we go, right? This would be a real pain to actually have to do using the definition, but using this table of common Laplace transforms, plus the fact that the Laplace transform is linear, distributing over addition and past constant multiplication, we're able to compute the Laplace transform of this relatively complicated function very quickly into this. All right, now at some point we'd like to get to link this to differential equations. And as we'll see, there's a really great and very sort of beautiful use for Laplace transforms translating differential equations into algebraic equations. But before we can talk about that, if we are able to translate a differential equation into an algebraic equation using the Laplace transform, just like any other transformation or substitution, at some point we're going to need to get back to where we started. So we do need to briefly talk about what is called the inverse Laplace transform. So let's go ahead and define that. So the inverse Laplace transform, it has a pretty simple definition. We're going to literally define it as the transformation that brings us back to where we started. So the inverse Laplace transform of a function of s is the corresponding function of t, such that if you were to apply the normal Laplace transform to that function of t, you would arrive at f of s. Notice what that basically means is that if in our notation we start with f of t, if we apply the Laplace transform, we imagine getting capital F of s in that new variable. If we were then able to use the inverse Laplace transform, we would return back to f of t. Now, we want to make a note here that just like we were seeing that the knowledge that a transformation is linear is incredibly useful, and luckily the inverse Laplace transform is also linear. So in other words, the inverse Laplace transform of the sum of two functions is the sum of their inverse Laplace transforms, and the inverse Laplace transform of a constant times a function, the constant can be brought out and you can simply apply the inverse Laplace transform of that function. Now, we're not going to prove the inverse Laplace transform is also linear, but once again, it should make sense. If the main transformation is linear and you're going to revert it, then it should also be linear. If you've studied some linear transformations, you will know that if you start with a linear transformation, the inverse is always linear. So this is just a special case of that. Now, notice that we can talk about some common inverse Laplace transforms. This table right here should look familiar because all we've done is we've reversed how this one was written. So instead of having it written with t here and then changing into L of f of t, which is what our initial table was, now we're starting with the other side, f of s, and changing it into the inverse Laplace transform of f of s. If you notice, though, this is literally just the previous table flipped around, reminding you that these are our common inverse transformations. Well, let's go ahead and use that to determine the inverse Laplace transform of a given expression here. So we want to try to do the inverse Laplace of this 8s plus 7, so I'm having a little trouble saying that, s squared plus s, and then minus 2. Now you will notice that initially this expression doesn't look like any of these things. We could certainly break this apart as 8s over s squared plus s minus 2 plus 7 over s squared plus s minus 2. But even if we did that, neither of those, like that 8s over s squared plus s minus 2, that doesn't look like anything in this table either. So that's not going to really help us. Now, we might think that we're sort of stuck, that we don't really have any way to actually make use of this table and no easy way to do this inverse Laplace transform. But instead, we're going to make use of something, and this is very commonly used when working with inverse Laplace transforms. This is something you encountered back in algebra. You also encountered it probably in Calc 2. It's the concept of partial fractions, the idea of breaking a rational expression into pieces. So let's remember how we would do that. So this is what's called the partial fraction decomposition. 8s plus 7 over s squared plus s minus 2. We can factor that denominator and recognize it as s plus 2 and s minus 1. And then because these are distinct linear factors, it should be a constant over s plus 2 plus a constant over s minus 1. And remember that these numerators, they always have to be a degree less than the denominators. That's part of the decomposition rule. And so since these are linears, these must be constants here. Now, in terms of solving this, we'll focus on this here. Multiply both sides by that least common denominator, which is just this denominator here. You'll get 8s plus 7 is a. When you multiply this onto here, this and this cancel, so we're left with just the s minus 1 plus b, and when we multiply this whole thing on here, this and this cancel, so we're left with b times s plus 2. Now you can technically set this up as a system of equations by matching up like terms, but in the case of distinct linears, most people like to just plug in clever values. So notice that if we do like let s equal 1, then on the left-hand side, we'll go ahead and get 15, and then over here, we'll get that a times 0 plus b times 3. And notice that that'll get a 15 equals 3b, and for free, we get b equals 5. And then if we go ahead and let s equal, say, negative 2, then on that left-hand side, we'll get negative 16 plus 7, that's negative 9, a times negative 3 plus b times 0. And then that should give us negative 9 equals negative 3a, and that gives us 3a equals a. So we now know that an equivalent way of writing this is we're trying to do the inverse Laplace of 3 over s plus 2 plus 5 over s minus 1. Now this is a lot more sort of encouraging as an expression, because if we look, these types of denominators are something that we have an inverse Laplace of. This plus is no issue because the inverse Laplace is linear. So we can go ahead and distribute it over the addition. So we'll be taking, we'll put our equals there to be a little bit more clean with our notation. There we go. We can pull those constants out. 1 over s plus 2 plus that 5 times the inverse Laplace of 1 over s minus 1. Then we simply say, okay, this, well, that inverse Laplace of 1 over s plus 2, that looks like this. 1 over s plus 2 can be viewed as 1 over s minus negative 2. So the a is negative 2. And this should become 3e to the negative 2t plus the 5. Same thing on this one. Look up here. See that? 1 over s minus 1. The a is 1. So that would be 5e to the t. So our inverse Laplace of this rational expression is this sum of two exponential functions. So that, again, that linearity of the Laplace transform and its inverse, super essential for being able to make use of that table and avoid having to use that ugly sort of definition of that improper integral. Okay, we are almost ready to apply this to a differential equation. But if we're going to do that, we now know how to use the Laplace transform. We now know how to use the inverse Laplace transform to get back to the variable we started with, but we have to talk about how the Laplace transform interacts with the derivative. So let's talk about the Laplace transform of the derivative. So let's see if we can determine what is the Laplace transform of the derivative of a function. Well, this is an investigation, so the only place we have to start is to actually use that definition. So keep in mind, back from our very first thing we discussed, that the Laplace transform of the derivative is going to be the integral from 0 to infinity, the derivative times that e to the negative st dt. And we'll go ahead and write that as the limit as some parameter r goes to infinity, integral 0 to r, f prime of t e to the negative st dt. Now, we don't really know much about this, and we're not really hoping to get just like a single answer, but we're just trying to see what we can find as we do this. This doesn't look too promising, but maybe we can try one of our integration techniques. This is a product of two things, so let's go ahead and try that old technique, integration by parts. So we're going to choose a u and a dv. Now again, in integration by parts, there's no rule about which one has to be placed here or something. But keep in mind that whatever you put as u, you're going to end up differentiating to du. And whatever you put as dv, you're going to end up taking the integral to getting to v. But notice we know something about the integral of f prime. That would get us back to the original function f. So let's try putting f prime of t dt here, and then sticking the e to the negative st as our u. Du then, remember we're differentiating with respect to t here, so it's going to be negative se to the negative st, because we're treating s as a constant. And of course the antiderivative of that f prime of t is f of t. So we now have this as the limit as r goes to infinity, parentheses, following your integration by parts, this times this. So we would have e to the negative st f of t, and then that would be evaluated from 0 to r, minus the integral from 0 to r of this v du. So that would be our f of t times negative se to the negative st dt. Okay, so we're going to move this a little bit over to here since we're sort of getting down to where our next thing is written. Let's go ahead and move this over to here. This is going to be our limit as r goes to infinity. Let's ignore this part for right now. We'll just keep it as it is and we'll deal with it in a moment. But let's go ahead and simplify this. There's double negatives, so we'll just make that a plus. And let's bring this s out here. We can do that since it's an integral with respect to t. That s is just being treated as a constant. So let's go ahead and bring that out there. So we'd have plus s times the integral from 0 to r, f of t e to the negative st dt. And this is the first sign that we're really learning something important by doing this, right? So far, all this stuff might just seem like a lot of sort of work, like we're just sort of pushing stuff around, like where is this really headed? Well, it's really headed to recognizing this right here. This right here, if we imagine that limit as r goes to infinity, that's basically making that guy an infinity. That means we have the integral from 0 to infinity, f of t e to the negative st dt. That is literally the definition of the Laplace transform of f of t. So we can replace this as the limit as r goes to infinity. We have this e to the negative st f of t 0 to r plus s, and now we know we get the Laplace transform of f of t. So we've established a relation between the Laplace transform of the derivative and the Laplace transform of the original function. We just need to figure out what's going on with this. So let's go ahead and plug in those bounds. So we'll get this as the limit as r goes to infinity. We'll just shift over a little bit, put our parentheses, e to the negative sr f of r minus e, we're plugging in 0 here. So if we think about plugging in 0 for t, that's going to just become a 1 because it's e to the 0. So we'll just be left with f of 0. So minus f of 0, and then plus that s times the Laplace transform of f of t. The only thing that sort of stands out is that we don't know what's going to happen with is this. But this is where we're going to use that definition of f being of exponential order. Remember that if f is of exponential order, then this expression here will converge to 0. It'll go to 0 for some s greater than a. So we can assume that this guy is going to go to 0. If he doesn't go to 0, then it's diverging, and this Laplace transform isn't well defined, doesn't make sense here. So this piece here, this is going to go to 0 since f of t is of exponential order. If it's not of exponential order, then its Laplace transform doesn't even exist, and writing something like this doesn't make sense. And we end up, well, if we just write that by sort of changing it into a nicer looking format, s times the Laplace transform of f of t minus f of 0. So we have a relation that says if you wanted the Laplace transform of the derivative, you can write it into something that is related to the Laplace transform of the original function with a constant here based on the function's original value at 0. All right, now this was sort of a messy derivation using integration by parts, so let's just have that result summarized sort of nicely right here. The Laplace transform of the derivative is s times the Laplace transform of the original function minus the original function at 0. It turns out you can extend this result. I'm going to spare you the sort of computation. It involves, again, just an integration by parts and the use of this previous one. You can extend this result to how the Laplace transform applies to the second derivative, and you get a result that looks like this. Obviously, it does not end at looking at the Laplace transform of the second derivative. You can continue on in a similar manner, building the Laplace transform of any order derivative. For the purposes of this video, we're just going to talk about the Laplace of the first derivative and the Laplace of the second derivative. So, without further ado, let's see how this helps us actually solve a differential equation, specifically an IVP. So, we're going to look at using the Laplace transform to solve an IVP. We're going to try to solve this pretty simple IVP, y prime plus y equals 2 sine x, with the initial condition of y of 0 equals 0. Now, this one, if you've studied first order differential equations, this you can easily sort of solve through using something like linear differential equation. It is linear. You can use an integrating factor, all that sort of stuff. So that we're not saying that the Laplace transform is the only way to approach this, but let's see how we could use it to approach this. So we're going to apply our Laplace transform to the differential equation. So let's see how that would work. So we would take our Laplace of y prime plus y equals the Laplace of 2 sine x. Now, as we know, the Laplace distributes over addition since it's linear. So it's the Laplace of y prime plus the Laplace of y. And over here, we know it distributes past constants. So that is 2 times the Laplace of sine of x. Right? And notice that even though we're using the independent variable x here, right, we'll be treating x as t. And then when we actually go ahead, we'll still change it into s, and we'll change it back into x later on. Now, from what we just learned, we know what the Laplace of y prime is. If we look back over here, that Laplace is going to be s times the Laplace of y minus that f of 0. So let's go ahead and write that. This right here, from what we saw earlier, this is s times the Laplace of y minus y at 0 plus the Laplace of y equals, and then maybe for color coding, let's write the other, keep the others in sort of black here because we're only using that what we learned on the previous bit on that part in red. And then over here we have 2 times the Laplace of sine of x. Okay, now this actually we can do even better because of our IVP. And this is why Laplace transforms work super nicely with IVPs. This minus y of 0, we can literally replace right with that, and we can replace that down to whatever the initial condition was. So this will simplify. So using IVP, we now have this as s L of y minus 0 plus L of y equals 2L sine x. Okay, so on this side we have s times the Laplace of y plus the Laplace of y equals, well, now it is time to go ahead and do this Laplace of sine of x. Going back to our table a little earlier, there we go. Sine of x should be, with a being 1, should be that 1 over that s squared plus 1. So we'll go ahead and put that in. So this is going to be 2 times 1 over s squared plus 1. Okay, now, at this moment, this is the first time we've been using the Laplace transform on an IVP, on a differential equation. So what is the point of this? Well, we haven't solved it yet, but notice that we have an expression here. We have an equation. We're still trying to solve an equation, but this is not a differential equation anymore. This is an algebraic equation. There is no instance of the derivative anywhere in here. This is an algebraic equation, and we are so much more comfortable, regardless of your study of differential equations. We are much more comfortable solving algebraic equations than we are solving a differential equation. So let's go ahead and solve this. We're going to isolate the L of y, the Laplace transform of y. So that would be s plus 1 times the Laplace of y. And we'll just write that as 2 over s squared plus 1. And then that would give us our Laplace of y is 2 over s squared plus 1 times s plus 1. Okay, now we've isolated our Laplace of y. Now we can apply the inverse Laplace transform. And we can get that y is the inverse Laplace of 2 over s squared plus 1, s plus 1. Now, if we can figure out what that inverse Laplace transform is, we will be all done and we will have solved this IVP. Looking back at our inverse Laplace table, denominators like s squared plus 1 and 1 over s plus 1 are good. We just need to have them in separate terms so that we can make use of that linearity. So we're again going to do a little partial fractions work, right? So we'll write this maybe in a different color here. We'll do this in green up here. So we're going to do a little partial fractions work on this here. So our partial fraction decomposition, 2 over s squared plus 1, s plus 1. This decomposition is going to be as plus b over s squared plus 1. That is because s squared plus 1 is an irreducible quadratic, plus c over s plus 1. Multiplying by that least common denominator, we're going to get 2 equals AS plus B times S plus 1 plus C times S squared plus 1. Okay, a little bit messier than the last time. We can still get a value for free. Let's go ahead and let S equal -1. Doing that, we get 2 equals. S equals -1 makes that 0. Drop all that out. Over here, we're going to get C times 2, and we get C is equal to 1. At this point, we're going to have to probably do the rest algebraically. So 2 equals, well, that doesn't look very good. Let's do that real quick. 2 equals, don't know why it doesn't want to write right there. One moment. 2 equals that AS plus B times S plus 1, and we know C is 1, so we have plus S squared plus 1. Go ahead and multiply this out. You'll just have to FOIL that. Looks like you get AS squared. Looks like we get plus BS plus AS plus B plus S squared plus 1. Matching up some like terms, right? If we look at like the S squareds, on the left-hand side, there are no S squareds, so we have 0. On the right-hand side, we have A plus 1. That tells us A is -1. Looking at, say, the S equations, for the S equations, we have no S's on the left-hand side, so we have 0. And then we have B plus A on the right-hand side. That tells us since A is -1, we get 0 equals B minus 1, and that tells us B is 1. So going back over here, we actually know now that our y is the inverse Laplace of, well, in our form, it would be negative S plus 1. Again, some writing issues. My apologies there. We're just going to switch styluses real quick. Okay. So we'll just go back real quick. Minus S plus 1 over S squared plus 1. That's just coming from this portion here based on our A is -1 and B is 1. And then we found C is 1, so we have plus 1 over S plus 1. All right, we'll take this onto a new page real quick. Let's go ahead and just finish this up. We're almost done, so we'll just copy this over. All right, let's copy that right here. Just make that a little bit larger. Our y then, well, just like in normal partial fractions, let's break that up a little bit more before we go forward. Let's make that negative S over S squared plus 1 plus 1 over S squared plus 1 plus 1 over S plus 1, just breaking it into each component. That's great for the inverse Laplace because it distributes to each of these. Notice, just combining a couple steps together, this is going to be negative the Laplace of S over S squared plus 1, because we can factor that constant negative outside, plus the Laplace of 1 over S squared plus 1, plus the Laplace of 1 over S plus 1. What does that give us then? Well, looking back at our table of inverse Laplace, this guy right here, Laplace of S over S squared plus 1, S over S squared plus 1, that is this guy here with A is 1, so that is a cosine. We won't call it T though, we'll call it X. So that is negative cosine X plus this guy, looking back at that inverse table right here, a number over S squared plus A squared, that is sine with A equals 1 again. So that gives us a cosine, or a sine, excuse me, of X. And then this last one here, well, we've seen this a couple times. The Laplace of that 1 over S minus A is equal to e to the AT. Here the A is -1. So we get an e to the negative t there. or sorry, negative x. My apologies. There we go. And there is our solution, negative cosine x plus sine x plus e to the negative x to our IVP. You can go ahead and check, right, that it works if you want by plugging it in to the differential equation and making sure you do get 2 sine x. You can also just quickly confirm that it does satisfy y of 0 equals 0. If you plug in x equals 0 to this, you'll get minus 1 plus 0 plus 1, which does equal 0. So this guy, you can check, does satisfy the differential equation, and you can easily check that it meets the initial condition. Let's go ahead and try this once more with a second order differential equation. So for our last example, here is a second order IVP. Again, depending on your comfortability with having learned about solving differential equations directly, this would be classified in some textbooks like the Good and Annan Linear Algebra and Differential Equations textbook as a case 2. And what that means is that it's missing the independent variable x. You can attempt to solve this one that way, and while it does proceed forward, you get to a integral at one point that is very, very challenging to do unless you have sort of specialized knowledge about how to approach it. And so actually this is a second order differential equation that, while it classifies as something we might have encountered a way to solve, it isn't necessarily easy to do so. With the Laplace transform, though, it won't be too bad. So let's go ahead and try this by applying the Laplace transform on both sides. So we're applying the Laplace on both sides. Then, because it's linear, we can distribute. And again, we'll sort of jump ahead a little bit by distributing it over the addition and pulling out the constant multipliers. Okay. Let's go back and use our result on this. We stated that back when we were talking about using the derivative. We said that that should come out as this expression here. So let's go ahead and do that. So we'll take that here. That is going to become s squared, the Laplace of y, minus s and the original function y at 0, minus the original function at the original function's derivative, not second derivative, at 0. Let's just go back and check that. Right, that's right here. And that is what we wrote down, minus s f prime of 0 minus f double prime at 0. Did we mistype that over here? Yes, this should be f of 0. My apologies when we wrote that down, and this should be f minus f prime 0. My bad, this is a typo back there. We'll go back and fix that later. So let's go ahead, go off of this. This is correct here. Minus this, now we have 6 applied to this one here, which is s L of y minus the y of 0, right? This is making use right here of what we saw earlier that we derived, that we know is correct, this right here. So we've got that guy. And then finally, we have our plus 8L of y equals L of 8. Okay, our Laplace transform of 8. Let's simplify this a little bit. We get s squared L of y. Here, we know what y of 0 is. It is 1, so that is going to be minus s. Here, we know what y prime of 0 is. This is 2. And that's why this works so well with IVP. So we get minus 2. Over here, we get minus 6s L of y. And then this would be minus 6 on here. It's going to be plus 6. And since y of 0 is 1, we'll get plus 6. And then we have plus 8 L of y. And then it's probably time to go ahead and do this transformation, L of 8, going all the way back to when we first introduced our common transformations. Well, 1 is 1 over s, so 8 is going to be 8 over s. So we've got that there. That is going to be 8 over s. Okay, so we've got that. Let's go ahead and isolate our L of y. So s squared Laplace of y minus 6s L of y plus 8L of y. Bringing everything else over, looks like we're going to have s. And then looking at this, minus 2 and plus 6, that is going to be plus 4. So when we bring it over, we get minus 4. And we have our 8 over s here. Okay. Let's go ahead and put this together as one sort of fraction. So let's take a moment to do that just by making a common denominator. Ly. Let's go ahead and do that. That's just going to be s squared minus 4s plus 8 all over s. Okay. Now we'll do a little factoring. We'll get our s squared minus 6s plus 8 times our L of y equals this whole thing over here. And then do our division. L of y, s squared minus 4s plus 8 over s squared minus 6s plus 8. And then notice, right, we can say that y is simply the inverse Laplace of this rational expression. Now, of course, as we've seen, to actually do this, to actually perform this inverse Laplace here, we are going to have to go ahead and actually use some partial fractions knowledge. So we'll go ahead, we'll grab this for a moment. Let's give ourselves a new page. Right, let's do our partial fraction decomposition. Right, this s squared minus 4s plus 8 over, well, let's factor that. That's going to be, well, s minus 2 and s minus 4. And that means the decomposition is going to involve 3 pieces, 3 distinct linear pieces here. Remember that the number of unknown constants always matches the degree of your denominator. Third degree here, so we have 3 unknown constants. Multiplying by that least common denominator, we do get a times s minus 2, s minus 4, plus b times s and s minus 4. We'll just have to scoot this over just a little bit since we're running out of some space there. And then plus c times s and s minus 2. This one will be easy by just choosing some clever values. Let's go ahead and let s be 0. So if we let s be 0, left-hand side becomes 8. This and this are going to drop out. We're going to get a times minus 2 times minus 4. And that looks like we're going to get 1 equals a. If we let s equal 2, left-hand side, that's going to be, what, 4 minus 8 plus 8. So we'll get 4. This one will drop out, and this will drop out. So we'll just get b times 2 times minus 2. So it looks like b is negative 1. And then let s equal 4. Over here, 16 minus 16 plus 8. So that's going to be 8. And then over here, since s is 4, this and this drop out. And we get c times 4 times 2. And then that looks like we get c is 1. So our actual decomposition is going to be 1 over s minus 1 over s minus 2 plus 1 over s minus 4. Bringing that back over, that means our y is actually the Laplace inverse of 1 over s minus 1 over s minus 2 plus 1 over s minus 4. That's what we saw back here. Yep. And then we know that the inverse Laplace is linear, so we can view this as breaking up into these pieces. And going and doing each of these, 1 over s. Well, if we go back to our table of inverse Laplace, 1 over s, that corresponds to 1. So if we go back over here, that gives us a 1 minus. we know that this is going to come out as e to the 2x. This comes out as e to the 4x. So there is our solution. Y equals e to the 4x minus e to the 2x plus 1. Now, at the end of this video, you're probably looking at this and your main focus is on thinking about the partial fractions, the computation, everything like that. In terms of doing Laplace transforms at this level, that is generally the sort of manipulations you need to be comfortable with. But as an idea, the big idea here is about the concept of the Laplace transformation changing what is originally a differential equation into an algebraic equation and solving it through algebra. At no point do we actually do any sort of integration here, even though we are solving a differential equation. That is really philosophically the idea of a Laplace transform. So that's it, a brief introduction to Laplace transforms. Hopefully you enjoyed the video, and we'll continue exploring how algebra can help us solve differential equations as we move forward in our course.